Hello everyone, I am Yixuan and I'm going to present to you an iterative spectral unmixing method for spectroscopic photoacoustic imaging. Photoacoustic imaging has become an important modality in many clinical applications. In quantitative photoacoustic imaging specifically, we're interested in estimating the concentration of different tissue types. The estimation starts from reconstructing the measured photoacoustic signal P of t to the initial pressure P null in the acoustic inverse problem, followed by the estimation of gradation parameter, the optical light fluence, and spectral unmixing sequentially in the optical inverse problem to finally get the concentrations. A critical challenge in quantitative photoacoustic imaging nowadays is the estimation of optical fluence in deep tissues especially, because there is not yet a device to do so. In this work, we propose a novel iterative spectral mixing algorithm for fluence compensation in the optical inverse problem. We employ the prior optical information of tissues and computation power of simulations. After initializing the variables and inputting prior information, including spectral characteristics, illumination pattern of the light source, and gradation parameters, we first run the Monte Carlo simulation to estimate the light fluence distribution, then calculate the initial pressure and compare it with the measurement. If the estimation is not close enough to the measurement, then we update the optical absorbance, run the spectral mixing to estimate the concentrations, and update optical properties based on the concentration. We run the whole process iteratively until the estimated initial pressure is close enough to the measurement. We validated the proposed algorithm in simulation. The ground truth is synthesized from in vivo data, where cross-sections of a control prostate tumor and a target prostate tumor on the lower back of mice were imaged. Details about the in vivo data can be found in the following reference. When synthesizing the ground truth, we assume the end members of interest are oxyhemoglobin, deoxyhemoglobin, a prostate cancer targeted contrast agent, and water. Optical parameters such as absorption coefficient, scattering coefficient, and anisotropy were either measured on a spectrophotometer or acquired from the literature. Let's have a look at how the fluence was compensated. The concentration of all end members are initialized as 0. So in the first iteration, Monte Carlo simulation returns illumination pattern of the light source itself. Then as the algorithm iterates, the estimated fluence becomes closer and closer to the ground truth. As we can see, after around 4 or 5 iterations, the estimated fluence is already very close to the ground truth. As for the spectral mixing result, we can see the unmixed contrast agent also gets closer and closer to the ground truth as the algorithm iterates. And the algorithm converges well. Note especially at the arrows in the animation that those indicated artifacts disappear after 3 or 4 iterations. We further compare ISU, the iterative spectral mixing, with the scenario of no fluence compensation, shortened as NFC. Comparing with the ground truth, 15 test data reveals that ISU showed significantly lower root mean squared error and higher Pearson correlation coefficients than NFC in all types of end members. In conclusion, in this work, we proposed an iterative spectral mixing method using multi-wavelength information and prior knowledge to quantify tissue concentrations. The ISU method converges well and shows very high spectral mixing accuracy. One remark is that to translate ISU to in vivo and clinical applications, accurate prior knowledge about optical properties of tissues of interest will be critical to success. Thank you for your attention.